So what you just saw was that we can exploit the characteristics of an array or the property of constant access in an array to actually create a hash table. So let's discuss the time complexity of the common operations, which is both insertion and find, as we discussed in the previous video, is going to be constant, because essentially what we are doing is we are looking up the value really fast at a particular index in an array. So what is the bigger problem of this approach, which is like, let's say if I were to discuss what is problematic with this approach, is there are two big problems. First, it actually wastes a lot of memory. So like, let's say if we had 100 elements and we knew that the range of elements starts from, let's say, 0 to a billion, we would be wasting more than like 99% of the space to actually consume a very small range of numbers, which is, you see, like we are storing all these false, but they are actually not required. The second big problem was, how does it work for data types, which is like, let's say if this was very simple, which is the integers actually mapped to indices in an array. But let's say if I wanted to store a string, like let's say cat or dog, or if I wanted to store a user-defined data type or a big file, how would I store that or map that at a particular index in an array? So that's what we are going to see now, and we are going to kind of like abstract the data structure for more and more data types, and the end result is going to be like a hash table when we solve all these different problems that we encounter. But essentially what is a hash table is nothing but storing values into an array or a table for quick insertion and retrieval. So let's try to understand how do we deal with another type of data, which is like, let's say if this was strings. So we are trying to first solve this problem of what if there are other data types. So let's say if I want to store cat or dog, how we can represent them. So there could be like a lot of different approaches, which is like, maybe what we can do is we can just look at the first letter of this particular string and discuss, or maybe convert this into an integer, which is, we know like we have alphabets from A to Z. So essentially C will map to 3, D will map to 4, and so on. And we can again use like constant access, which is we can store at position 3 in our array cat and in position 4 dog, or so on, to represent this. Now basically what we are trying to do is we are trying to convert our data type or any type of data that we have into a number, and that is actually the first big component of a hash table, which is essentially to turn the data type into something called an index or a position in a hash table with the help of something we call it as hash function. So essentially what we are trying to do is we are converting this data into a number. So as we use this approach, that let's say if we just had lowercase letters in our data, which is A to Z, what we can do is we can represent A with 3, A with 1 and Z with 26, and we can store these values into the hash table, which is cat and dog. We are just assuming that we have actually changed the flag from false to true. But again, like, what is the problem with this one, which is like, let's say if now we have another string that starts from C, which is like, let's say if you have cap, caption, carpet, or even like CT scan, so on. So if you have all these strings, what will happen is, like, let's say if I have another string carpet and I have this representation of all these different strings in the form of a set, which is I now have a set that is actually represented with 26 different buckets or 26 different locations, and each location maps to a particular string, the first alphabet of the string. Now if I have like cap, and if I want to search cap into this set, what I'm going to do is I'll extract this first letter, turn that into a digit, which is now it's going to be 3. I'm going to see if the value at the digit is actually true. So that's the case. So I'm going to return true, which is cap is there in this database. But actually it's not there because we just stored cat. And essentially, like if we have overlapping words with the same alphabet, same starting code, essentially we'll have something called collisions, which is we will map to a certain index into our array, which represents more than one or like many different forms of data. So let's see how we can improve on this, which is like, let's say if I want to represent strings, like this approach is pretty naive, it's not going to work. So the idea here is that like how we can avoid like this collision is by using different forms of representations, which is the idea we are going to use is we are going to multiply all the digits with the powers of 27, which is, this is a method that I'm going to first describe, and then I'm going to also discuss like where did it actually come from. So actually forget about these strings. Like let's say if we have numbers, like let's say if we have like 1011, 115, we talk about this decimal system. So we actually represent numbers in the form of the powers of 10, which is in this case, like let's say if we have 10, like let's say 17, what we essentially do is we have 10 to the power 3 multiplied by 1, and then plus 10 to the power 2 multiplied by 0 plus 10 to the power 1 multiplied by 1, and then 10 to the power 0 multiplied by 7. If we sum all of these, we get like 1017. So essentially you have these digits and you're multiplying each of these digits by powers of 10, which are increasing from from right to left. So essentially this is what we are trying to do. So we use the same approach, which is like whenever we have like these numbers, like let's say if it is 115 1017 or like a trillion or 5 and so on, we can never have the same powers that represent two different numbers, which is you can never have same equating powers. Like let's say if I represent these numbers, each number will have a different representation or different indices that you will see for a number representation. So for a string, what we do is we use the same concept, but instead of multiplying by 10, because essentially they were 10 digits from 0 to 9, what we are doing here is we are actually multiplying them with powers of 27, which is you can take any number that is greater than 26, because there are 26 lower case alphabets, which is from A to Z, or you can also take 26, that's fine, but I'm taking just an arbitrary number, which is 27. And what I'm going to do is I'm going to convert this string into a number, which is essentially what we did was like each of these values here, the letters are first transformed into values, which is C is 3 as per our previous definition, A is 1, and T is 20 by the same logic. Okay, and what we do is we multiply each of these just how we were multiplying numbers, but instead of multiplying with base 10, we are multiplying with 27, and it'll get more clearer as we go forward, which is you multiply this one with 27 to the power 0, this one with 27 to the power 1, and this one with 27 to the power 2. So essentially you'll get a representation that looks like this, which is 2, 2, 3, 4. That is for cat. Now let's say if this was another one, like let's try to do another example. So let's say if this was just a 2-letter word like on, a preposition, what we are going to do is we are first going to identify what are the values of O and N. So J is 10, K, L, M, N, and O. O is 15, JKLMN. So O is 15 and N is going to be 14. And what we essentially do is we multiply 14 with 27 to the power 0 and 15 with 27 to the power 1. So what we'll get is 27 into 15 plus 14 into 1, which is going to be, if I multiply this, this should be 135. No, I think this should be like 105. Yeah, 105, and 15 2 is a 30, 40. So 405 plus 14, this should be 419. I'm just going to use a calculator real quick to make sure I'm multiplying these correctly. So it's 405 plus 14. Yeah. So the exact representation of our sequence of characters like on is going to be 419, but you get the sense, right? So I'm going to make a claim that no two words, like let's say if you have cat, let's say if you have dog, or if we have a very long string, no two words can actually have the same end result value, because this is using the same concept that we saw for numbers, which is if you're trying to calculate numbers, we use these power of 10 method. Now we are using power of 27. So let's go to the next one, which is to fix this, we use all the digits by multiplying each of them with the power of 27, which is the index of cat. We saw it's equal to 2234. Now here I want to again reiterate the fact that as long as the base is greater than 26, we will never have a collision. And we are only talking about letters from A to Z. I'm not talking about 0 to 9 or like capital A to Z, because if we have like a larger number of larger variants in our data, what we need to do is we need to increase this value further, which is like, let's say if we have 0 to 9 plus like A to Z, so I think the minimum number of base that we would require is like 36 or greater than that. If it is less than that, then there will absolutely be a collision. Like that is also true, which is it uses the fact, like in mathematics, there's a principle that's called a pigeonhole principle. It's pretty straightforward, which essentially what it states is, like, let's say if we have a box that has like 9 smaller boxes and we want to fit 10 pigeons in it, there will be at least one box that will contain more than one pigeon, which is essentially like the same principle is being applied here. Like, let's say if we have some spaces that are there in a hash table, and if we have, like, let's say we have 100 spaces in our hash table, and if we have 105 values, what we are essentially saying is we are guaranteed to have like 5 collisions. Okay, so that's the entire gist of it, which is, I'll give you another example here, which is here, if instead of a particular base, which is instead of the base 26, if we had used this other base, which is base 2, okay, so in this case, the index of A, C, and E would actually land to be 5. Okay, the total computed value based on this logic. But if this was base 27 or even 26, like whatever value we chose, they will be guaranteed to be different. So we don't deal with the proof of this, but like it is actually based on pigeonhole principle. If you do not understand this, feel free to refer to some of the books, but the idea is generally the same, which is power of 27 or a power of a number can help you generate, like represent a string into another form. So the key idea here is that, like, let's say if we have a lot of different characters that are represented, we already have predefined tables like or conventions, which is we saw ASCII in programming 1 and 2, which is essentially in an ASCII table there are 0 to 127 or 128 different characters. In Unicode, that number is pretty large, which is it has more than 100,000 characters. So what we can do is we can generate this table even larger, which is for an entire ASCII set. What we can do is to represent, like let's say if you have a string like this, which is Aman 123 $hash new line and whatever. So what we can do is we can multiply each of these digits, like convert these digits into its ASCII value. So I don't remember the ASCII values, but let's say if it is A's ASCII value, I remember that this is going to be 97. So I just multiply these values with this, the total number of characters in a data set, which is 128 to the power, like let's say this has, right now it has like 9 different characters. So essentially I'm multiplying 97 with 128 to the power 8 plus m would be somewhere around, let's say 112. I don't remember the exact value, but let's say if it is 112, so it's 128 to the power 7, and you add all these values to get a very, very large number. Like it could be a long string, but that's the gist of it. But it's going to be absolutely unique. There will be, we are never guaranteed, we are guaranteed that there will be never a collision. So this is how we actually solved the first problem, which is we fixed the problem of storing other data types, which is we can store any data types. But now the problem is that the value that we get from this hash function, which is we represented strings, or we converted these strings into integers, but the integers itself are so large that we have to deal with the problem of overflows. Also, the tables will now be even larger, so we are wasting a lot more space. So now we fixed one of the problems, which is we can now store any type of data, which is like string or anything like that. But the issue is we are wasting a lot more space, and we also have collisions, not because of like the hash function giving us similar values, but instead because like if we have a very long very long string of digits, like 112579, we know like if we were to store the computation, the output of our hash function into an integer, this will not work because the range of integers in most languages is like roughly 2 billion, right? But these numbers are really large, so they will kind of like overflow and get back to like negative values, or they'll be always between some value. So again, this will result in collisions because two values that are really large, if they are wrapped around, or when we have like a range of a data type that's like an integer that has a range between 2 billion. So essentially, when we are treating overflows, what we are doing is we are computing the modulus of that overflow using the largest value in the range, which is we mod it by 214 billion or so. Okay, so sorry, 2 billion and 14 million and so on. So essentially, what we again come down to, like what this boils down to, is that we again are back to overflows, which leads to collisions, and we are wasting more space. But that brings us to how we are going to solve this in the next video, and we'll see how we are going to fix this.